Basic digital building blocks. This is primitive logic gates, multiplexers, arithmetic circuits, encoders, input outputs, Q0, Q0, Q1, Q2 output, T0 to T7 input, low priority this high priority, decoders, 7 segment decoder, 0 to 6, 0, 1, 2, 3, 4, 5, 6, 0 to 3, 7, 7 segment decoder, flip-flops and registers. Q0, Q1, Q2, Q0, Q1, Q2. Clock pulse. Primitive gates. We have the basic and OR, NAND, NOR, XOR and XNOR gates. Multiplexer mux. These are really useful components. Show here is a 2 to 1 mux with 2 data inputs and 1 select input. The output is one or the other depending on the select input. We often put a number of these together to provide multiplexing function to a multi-bit data word as shown here with the two 3-bit numbers. Arithmetic circuits. Commonly found are adders and multipliers. Subtractor can be built from an adder if we use 2's complement representation of signed integers. Encoders and decoders. These two are related. Encoding is a logic module that reduces encodes a large number of bits and produces fewer output bits. Decoders are the opposite. Shown here is a 7-segment display decoder where 4 input bits are decoded into 7 logic signals to drive the 7 segments of the display. The encoder here is known as a priority encoder. It produces a 3-bit output showing where the first one is encountered from the most significant bit D7 to the least significant bit D0. Flip-flops and registers. These are the building blocks for all sequential circuits. As will be seen later, we really only use one type of flip-flops, the D flip-flop. There are building blocks for sequential circuits as well. We seen later we really only use one type of flip-flop. This is the D flip-flop. These are all important components that all digital circuit designers need to be familiar with. However, nowadays we rarely design large digital systems at such a low levels. Instead, we generally try to express these building blocks in a more abstract manner in a hardware description language. As we will see in the later lectures, in addition to these basic books, we also have memory devices and the microprocessors. These are topics that we will cover towards the end of this module. Cause and effect. Input B going high causes X to low. High, low. Here 0, here high. Okay, this is for this is B. that is 0 here, this one here, 0 1 1. Then output here RP low. Now I okay here propagation delay. This time delay between a cause and input changing and its effect and output changing, assuming output load capacitance of 30 picofarad. Example 74AC00 advanced CMOS 2 input NAND gate. Minimum time A high to X low. T PH yeah, P P L H minimum 1.5 time, type 1.5, maximum 6.5 nanosecond. 1.5, 6.0, 8.0 nanosecond. TPHL and the TLPH refers to the direction that the output changes, high to low, low to high. All digital circuits exhibit propagation delay. Here it is shows the delay table for a discrete logic CMOS NAND gate. The delay would be in the region of nanoseconds. However, with the FPGA chips we use for this module, the internal gate propagation delay is approximately 100 ps, okay, which is much faster than discrete logic. As can be seen later, the gate inside FPGA is also much more complex than a simple NAND gate. Also note that propagation depends on the cause. Input rising or falling and the slope of the edge. And the effect output rising or falling. Delay also depends on what are connected to the output. That is loading, as can be seen in the example here. The rising edge A to falling edge X delay is lower than that of A falling to X rising. Note that I use an arrow to indicate the causes, the blend end and the effect the point end in a timing diagram. D flip-flop. Data clock. This one data clock output. Clock. Yeah. Okay. Data. Yeah. Output. Okay. D flip-flop. Input effect happens on the rising edge. Input effect happens on the rising edge. Yeah. Rising edge. This is the rising edge. That's it. C1, C clock input. C clock input 1. This input number is 1. C1. 1D data input. 1. This input is controlled by input number 1. D. 1, 0, 1, 0, 0, 1, 0, 1, 0, 1. The meaning of a number depends on its position. A number after a letter is used to identify a particular input. A number after letter. A number after letter. C1. A number after a letter is used to identify particular input. A number before the letter, before a letter means that this input is controlled by one of the other inputs. Okay. This one other inputs. Sorry, another one here. After a particular input, particular. D flip-flop. Cause and effect. Clock high when clock is high. Clock causes Q to change. After short delay. This is the delay. This is the only time Q even changes. This is the only time Q even changes. This is the only time Q even changes. Okay. The value D just before clock. The value D just before clock. Clock high is new Q. Propagation delay clock high to Q is typically 1 nanosecond. Propagation delay data to Q does not make sense since data changing does not cause Q to change. Ripple counter. Notice inverters on the clock and data inputs. Least significant bit of a number is always labeled 0. State diagram, not including transient states. Propagation delay clock low to Q2 3 cos 1 nanosecond equal to 3 nanosecond. Q0, Q1, Q2. Okay. According to this clock, Q0, Q1, Q2. Propagation delay. Okay. Synchronous counter. A register is a bunch of flip-flops with the same clock. A register is a bunch of flip-flops with the same clock. The individual flip-flops are rectangles stacked on top of each other. Only the top one is labeled. A register is a bunch of flip-flops with the same clock. Okay. The individual flip-flops are rectangles. Are rectangles stacked on top of each other. Only the top one is labeled. All shared signals. Example: the clock input go to the noticed common control block.